Temporal facing 3, Galilean Transformation versus Lorentz Transformation. I had to cut off my previous video due to some sound issues. You may recall that I was explaining how the Lorentz transformations, if you stretch the space-time diagram along the horizontal axis or smash it along the time axis, it essentially becomes a Galilean transformation. So if, for instance, I drew a space-time diagram with the time axis in seconds and the space axis in meters, the speed of light, which is 300 million meters per second, is basically a horizontal line on this scale. And the Galilean transformations are indistinguishable from the Lorentz transformations on this scale. On the other hand, if I take my time axis and mark it off in seconds, and take my horizontal axis and start marking it off in billions of meters, gigameters, and the speed of light will be a line with a slope of about 3 seconds per gigameter. And on this scale, there is a big difference between the Lorentz transformations and the Galilean transformations. So let's have a look at an animation that shows a continual Galilean transformation. I should warn you that this image has a lots of color and complex moving and rotating lines and figures. I warn you this because I have heard that certain individuals are prone to epilepsy when they are exposed to see certain patterns, but I really have no idea what those patterns are. Are you ready? Okay, then I will describe to you my first animation. In this animation, we see a continual transformation. We envision a red coordinate system where the red vertical lines are stationary, then orange, then yellow, then green, then blue, then purple, starting over red, orange, yellow, green, blue, purple. When they fade into view, the objects stationary in these coordinate systems are traveling from left to right. From the left in the past to right in the future. Our point of view is continually accelerating, so that those objects that were traveling from left to right become stationary for a moment when their world lines become vertical, traveling from past to future without changing their position coordinate. Then, before they fade out of view, we have accelerated to the point where they are moving in a direction to the left. None of the objects in this animation are actually accelerating. The straight lines from the future to the past indicate that they are standing still or moving at constant velocity. But from our accelerating point of view, their paths through space are changing. So that is called the Galilean transformation. Now let's look at another animation, except this time the vertical scale is changed from a small distance to a very large distance. We still see up here that we are becoming stationary with the green, blue, purple, red, orange, yellow, green, blue, purple coordinate systems. But instead of the events moving along straight lines, they're moving along hyperbolic arcs. Also, in the regions to the left and right, which were flattened to a horizontal line in the Galilean transformation, we see that the events that we would ordinarily call now are moving forward in time in the region that we're accelerating away from, and they're moving backward in time in the region that we would that we are accelerating toward. Over the last couple of days, I've made two other animations. They are both showing how stretching the distance scale smashes the hyperbolas in the distance axis into flatness. And so the Lorentz transformation converts into the Galilean transformation. Now, this video has quite a bit more animation in it than my others, and that sometimes means skipped frames so that the video and audio won't match up. So let's keep this video short, and in the next video, I'll finally get on to the analysis of the twin paradox using temporal phasing. Please like and share my video, and be sure and go out and visit www.spoonfedrelativity.com. Thanks for watching.